Okay, I pushed the recording button myself, so no one needs to remind me this time. All right, so last week we talked about the sort of fundamentals of what a function is, domain and range and how they work and what makes a function a function. Then we also looked at graphing a little bit and talked specifically about even and odd functions and kind of what that symmetry looks like, right? So we kind of dug really deep into x squared and x cubed as examples, and then looked at, just kind of some stuff I threw together, right? There's nothing particularly important about any of those other functions that we looked at, except we wanted to look at these properties. This week and this whole week, we are going to be looking a lot more at graphing, because a graph is, especially for those of you that, don't plan on like going and doing a bunch of math and stuff, right? A graph is a good, concise, kind of powerful way to communicate information that, you just need to know how to read it, and then you can kind of get a lot of ideas across. So this is the thing that, whatever you're going into, you're probably going to see visual data and stuff. So kind of getting into that a little bit. What we're going to look at first are a couple of kind of generic, basic function types, common function types that are going to kind of be with us all semester long, and we want to get to the point that we recognize. So there are 6 things here. Y equals 3, and 3 is just an example. Any constant, they're all going to behave basically the same way. Y equals x squared. We spent a lot of time with that one last week. Y equals x cubed, same story. And then the square root function and the absolute value. What I want you to do is take a couple of minutes and grab a calculator or pull up Desmos or something, graph these things. Go to a place that you've got like probably a full empty page in your notes, so you've got room for things. Graph, draw yourself a little sketch. Doesn't have to be perfect. You pretty much just want the shape and kind of where it is, right? And then find the domain and range from the graph. So sketch of the graph, because we want to get to the point where we recognize these when we see the graph, or when we see the function, we can kind of, call to mind an idea of what the graph looks like. And then find the domain and range for each. Yeah. Yes, sorry. I forgot to count you. Okay, sorry. Technical issues for a second. We're good to go now. Okay, so y equals 3 or any constant, right? 3, 5, 7, 2, whatever. Just a horizontal line, right? Constant value, so y is not changing no matter what x does. So what's the domain for that? Yep. The function doesn't actually depend on x in the sense that it's going to change at all. So nothing can sort of go wrong or like break that, right? So the domain's all real numbers. What about the range? All possible y values it can give back. Kayla?
Negative, infinity, and then you're gonna stop at 3.
So the 3 part I agree with, but what kinds of y values are you ever going to get back from this function? Like, what does that function do? It just gives you 3, right? Like, no matter what, the outcome of that is 3. The output, the y value is 3. So it's just 3. If I want to write just 3, well, it's one thing, which means I can list it. If I can list it, I just list it in curly braces, right? So it's just 3. Okay, what about y equals x? Straight line, right? Y-intercept is 0, slope is 1, looks like that. Domain and range. Yep. For both of them. Right, again, think through it, kind of the same way we talked about last week. I got one end pointing to the left, I got the other pointing to the right. Everything in the middle is kind of covered up, nothing gets left out or skipped over. That's all real numbers, and the same idea for the range, but sideways. X squared, we spent a bunch of time on last week. I'm just going to write this stuff down. Refer back to your notes from last week if you want some more detail there. This is an even function. Y equals x, by the way, is an odd function. It's got origin symmetry. Right, if you look at that, it's symmetric about the origin. The cubic, we also spent a lot of time there. So again, I'm just going to kind of go quickly through that. The shape, though, is the thing that we want to kind of take away from it at the moment. Again, that's an odd function. It's got origin symmetry and looks kind of like this, right? The square root function. Okay. Excuse me. Okay, the square root function, you may or may not be as familiar with. The graph on the quiz I just gave you was a square root function. You didn't need to know that then, but it looks like this. What's different about this than all the others we've looked at so far?
It has a beginning point.
Yeah, it has a starting point, basically, right? It doesn't just always exist everywhere. right? This is the one place of the things we've looked at so far that I don't have, sort of arrows going off both edges of the graph, right? This starts very definitively at 0, 0. So what's its domain?
Zero, infinity,
Yep. And the range?
same thing.
Same thing. Okay, why, can we make any guesses about why the square root function does what it does? Why does this one start, or, if you want to look at it from the other perspective, stop somewhere? Why does this one not exist everywhere? What kinds of things can you take the square root of? Oh, well, okay, let me back up. What is a square root? What does a square root do? If I say, what's the square root of, I don't know, 4? Why?
It's 2 times 2.
Because 2 times 2, right? So it happens to be half, but it's half in the like breaking it into 2 equal pieces sense, right? So like the square root of 9 is 3, because 3 times 3 is 9. Okay, so what happens then if I ask for the square root of -9? So I'm looking for 2 numbers that I multiply together that give me a negative, right? Right, but the square root means I want those to be the same, right? So it's not exactly just division. It's that I want a number that when multiplied by itself gives you the radicand is the fancy word, but the thing that you're taking the root of. Okay, well, this doesn't work because those aren't identical. 3 times 3 doesn't work because that gives you +9. -3 times -3 gives you positive because they cancel in pairs, right? So no real number is going to work to give you this, right? A square root means 2 copies, a pair. Well, if they're positive, it's positive. If they're negative, it's positive. So like I can't make that work. You get to be able to do this kind of thing, to be able to define it, you have to expand stuff in like a big way and introduce a thing called imaginary numbers that we'll talk about in like a month. So don't worry about it yet. But the point for right now is that I can't do this. And if I take the square root of something, I'm never going to get a negative number back as the answer for like the same reason, but from coming at it from the opposite direction, right? That's why the square root function, because when we graph things, we're talking about real numbers this way, real numbers that way. That's why the square root function appears to have a beginning point, right? Or have a place where, it exists over here, it doesn't exist over here. The domain is restricted. It's only defined for positive stuff or non-negative stuff because 0 is okay, but that's why it does what it does. We'll see some other stuff throughout the semester where like similar kinds of things happen, where something's defined in certain places and not defined in others because it would break, right? If I try to type the square root of -9 into a calculator, it's going to give me some kind of error message, right? Or something about it being non-real. When I say like something breaks math, right? That's kind of what I mean. Like it doesn't work, so the function's not defined there. Okay, and the absolute value looks like that. Kind of a lot like the square function, but instead of being kind of gradually, curving, it's straight lines and they meet in a sharp corner. But if we're talking domain and range, those look a lot alike. And that's an example of an even function. And we looked at some of those last week, absolute value stuff. Okay, the stuff that we need to take away from this for right now, for the next month or so through test 1. These things we want to be able to recognize their graph. So if I give you a graph like this, you know that it came from what kind of a function? I'm making my hands curvy. So it came from a square function then, right? Straight lines in a sharp corner, then you'd have an absolute value, right? So we want to be able to recognize the graph. So that if I give you a graph, like take the notes and flip over to the back. If I give you a graph of a thing and ask you to tell me about it, you can recognize like, oh, okay, I know what kind of function that is because I recognize the shape, right? They're all distinct enough that we can tell them apart. And also, if I see, say a square root function somewhere, like written out symbolically like this, I know, okay, that looks kind of like this. It starts somewhere. It doesn't exist all the time, right? So I kind of have in mind an idea of what it's going to look like. Come, test one time, there's going to be a problem somewhere where I'm going to give you a graph of something and ask you to tell me about it. So you're going to need to recognize what kind of thing it is, first of all. Okay, does that all make sense? All right, now what we're really trying to figure out right now is what happens when we make, relatively minor changes to the function. What does that do to the graph? So if instead of looking at y equals the square root of x, which I know now looks like that, if we look at the square root of x minus 1, that's a pretty minor change, right? I've subtracted 1 in with the x term there. So it's not going to change fundamentally like what it does or how it works or where it lives or anything like that. What it's going to do is just transform the graph slightly, right? Maybe move it around. Maybe some stuff will, kind of change the shape a little, but kind of preserve like the basic properties of what it looks like. So what we need to figure out, over the next couple of days is how stuff like this affects the graph of a function that we already know about, right? So a known function, I do something minor to it. How does that change things? Scan that QR code to pull up a graph that looks like this. There are two things here. One is the kind of parent function, the starting point, right? The default thing. That's f of x equals x squared. And we know what x squared looks like now, right? Everybody show me what x squared looks like. Something like that, right? Kind of a U-shaped graph. The name for the shape is a parabola. That doesn't matter really, but something like that, right? The other thing there, that's in red. I don't know if you can tell on the projector really, but that's the parent graph. That's going to stay there. That's like where you started, right? The other thing that's in blue, that's okay. Now I'm going to take that and change stuff a little bit, right? F of x plus a. So I'm changing something kind of in with the x value, right? Before the function does its thing, and then plus b at the end. What I want you to do is take just a couple of minutes and mess around with these one at a time, right? So mess around with a little bit and get a feel for what that does. Take it back to 0, mess around with just b for a little bit, get a feel for what that does. Do both of them if you want. Take a couple of minutes to just kind of fiddle around with it by yourself and get a feel for what you think is going on. Make a conjecture, which is just like an educated guess about what you think is happening. And then take a couple of minutes to talk to people around you and see, if you agree, if you explain it the same way or differently, and then we'll reconvene in 5 or so. All right. Somebody talk to me about what A does.
Shifts on the x-axis.
Okay. So if I make A, I don't know, 4, what happens? Goes over to -4. Okay. How can I see that it goes over to -4? Or what goes over to -4? Maybe. That point? What's special about that point? Some stuff, that we'll talk about later. For the moment, if I'm just looking at the graph, right, just looking at like visually, that's the one that's easiest to pick out, right? It's kind of more visually distinct than others. If I start looking at other stuff, I can't really tell this point away apart from that one all that well, right? But that one stands out. So it used to be at 0, 0. Now it's at -4, 0. Okay, so no, I think you said it moves it over on the x-axis. Right? Okay. Can we be a little more precise or specific about that? Moves how? I mean, it moves the same distance, right? Thankfully, like I changed it to 4, it moved 4. That's good. It'd be weird if 4 made it move, 3.5 or something. Like that would be awkward. Go ahead, Jake.
With the specific letters it moves, like A moves on the x-axis,
Okay.
so the y.
So what if instead of 4, I let A be -3?
So it shifts the opposite.
Okay, so it shifts the opposite way. It does move along the x-axis or left and right, but it feels backwards, right? Shifts kind of in the opposite way. I gotta remember to try to stop using the word right so much when I'm talking about left and right as just like an affirmation. Okay, so shifts horizontally or left and right. Horizontally also. But this one feels backwards. Right? It's kind of the opposite of what you expect. I added 4. Well, that feels like it ought to make everything bigger, which ought to make everything move that way because that's the positive direction, right? But instead, it moves the other way. So it feels backwards a little bit. Or it does to me anyway. I don't know. Maybe it doesn't to you. That's fine. So I'll write a question mark. But it feels kind of backwards to me. And, that's, I don't know, that one to some extent is like you just kind of have to get used to it thing a little bit. It always feels backwards to me. I will probably at some point in the next couple of days goof one up at some point and look at a +1 and go, oh, that moves to the right. And no, it doesn't. Like it moves the other way. That's okay. We just gotta, work with it a little bit. Okay. What about the thing that I've labeled B here? Where is that A term happening? Like if I wrote down the actual equation for what's right there, the function is x squared, right? And we're saying x plus 2 inside the parentheses. So that would be this, right? Like that's what the thing that's in there in blue, that's what that actual equation would look like. It's a square function where I've added 2 to the x term, the input term. Okay, so A is happening on the inside of what the function's doing, right? So either, grouped in a set of parentheses or whatever. If you want to think about order of operations, if I'm going to evaluate this, like do the arithmetic, then what happens first? Parentheses first, right? So anything that's inside a grouping symbol happens first. That would be this, then exponents, so then the square, right? So this would happen before that does. That's why it moves left and right, because you're changing the input, and the input is the x-axis, right? It also kind of helps to explain or maybe help you see a little bit why it moves backwards. If I'm adding to the x value before I do whatever the function does, what that's going to do is make everything happen a little bit earlier, which is why it moves to the left. If I take away, that's going to move 3 to the right. If I take away, it makes everything happen later because I'm sort of, pushing the the schedule, back a little bit. Okay, so this A happens on the inside, shifts left and right, feels backwards. What about B? Goes up and down. And probably, there we go. And probably feels a little more natural or like what you expect, right? I added 3, everything moved up 3. Well, okay, I'm talking Y values. If I add to them, of course they sit, higher, they move up. So this is happening outside the, grouping symbol, outside of the square, after the square if you want. Shifts up and down. Vertically. And this one, again, to me anyway, feels kind of more natural, feels right. So one kind of works backwards, the other doesn't. That's a bummer because we got to keep that straight. But hopefully, over the next few days, as we do a bunch of examples and you do homework and stuff, it'll start to kind of click into place. So if I let B be negative or subtract something, it's going to move it down in the same way. And again, how far it moves matches, what that value is, which is good news, of course. Okay. So here's 6 examples. They're kind of paired up in like function type, like 1 and 2, 3 and 4, 5 and 6. You see are the same type of function. So how is this? Well, first of all, what kind of function is that? Square. And what's a square function look like? Something like that. And what's different about this one? That +3, which is happening inside. There's a reason, and it'll kind of, start to make more sense over the next couple of days, why I'm emphasizing the inside versus outside thing so much. But it's happening on the inside, which means it's going to move this way. We're adding 3, so it moves to the left. Shifted left 3. If I take x squared and shift it to the left 3, does that change the domain? Because what was the domain? Right, what was the domain specifically for x squared? All real numbers, right? It's everything. If I take everything and just slide it over a little bit, who cares, right? Does it change the range? No. Good. Okay. All right, what about number 2? Same kind of function, but that's on the outside now. If that's on the outside, what's it going to do? Change the y, so it moves. If I look at the graph, it appears to move up. I don't think this is faster than just drawing it from scratch would have been. Crap. Especially if I did it wrong. We're just gonna, here we go. So this point would be 0, 3. And again, I'm really just using that as something I can keep track of, right? 0, 3, does that change the domain? No, right? It's still, if I squash the whole thing down to the x-axis, it still lands in the same place, right? Or it still like casts the same shadow. It still covers all the same x values. What about the range though? Yeah, the lowest point used to be 0. Now the lowest point is 3. Now I don't have any chart. I guess that crappy tiny piece of chalk is better than none. The lowest point used to be 3 or 0. Now it's 3 because we moved the whole thing up. Right. So something to keep in mind with all these, if there's a cutoff for the domain or the range for where it lives, if you start moving it around in that direction, that's going to move along with it. Right. That changes too. Okay, cool. Y'all tell me about 3 and 4. What kind of function are they? Square root. What's square root look like? Something like that, right? Sitting at the origin and going, sort of up and right into quadrant 1. Okay. So what's this?
It went up 2.
Up 2. Yep. And this one?
Left 3. 2. Okay.
Yeah. On the inside, So it's gonna be left and right, right's, backwards. So +2 is gonna move it left. 2, that means that sort of base, like starting point, that used to be at the origin, now it's at -2, 0. That changes the domain, but not the range. Okay, 5 and 6, you do on your own. Flip over to the back real quick. So I guess summary of what we've learned so far. Changing or adding something to the inside is going to shift things left or right, but kind of in the opposite direction than you expect. Which I think deserves a shrug emoji. Whereas adding something to the outside shifts things up or down. But again, that one, kind of works the way you expect it to, right? Adding something positive moves it up. Adding something negative moves it down, which is, again, probably more in line with what we think ought to happen. This, think of as, you're making changes to the X value, you're making changes to the input. That's why it affects things left and right. And then for, kind of deeper reasons why it moves backwards also. But adding something to the outside, you're doing whatever, being outside of the parentheses just means whatever the function is going to do, it does, right? The square root, whatever, it does that. And then you add 5 to it, right? So you take whatever that Y value would have been, you make it 5 bigger. Well, okay, that's going to make it sit up higher, right? That's why it does what it does. Okay, the stuff on the back here. There are 4 problems. I'm just going to kind of walk you through them real quick. The first one, here's a function. Y equals the quantity x minus 1 squared plus 3. What I want you to do is think about what the parent function would be. So basically, like, what's the shape of the graph? Where did this come from, right? Like we have been. What are these 2 parameters going to do to change that, right? How do those change what's going on there? And then what does that do to the graph? I didn't say sketch the graph, but sketch the graph, right? Keep track of, that, again, sort of convenient kind of handle point on the graph of the thing, see where that ends up. 8, same deal. I was a little more concise in the directions, but same idea there. 9, I want you to do all the same stuff, but now we're working the other direction, right? We're working backwards. These 2, you could start by just typing that into a calculator or into Desmos and looking at the graph and using that to help you decide. Here we're starting from the graph. So the first thing I have to decide is what kind of thing is that? Right? What type of function are we dealing with? Okay, now where is it? Now how does that affect the function? And what I want you to write down is basically the equation version of that, right? The symbolic form. And then 10, same idea, but instead of giving you a picture, I'm giving you a description, right? So just in English, I want you to do a thing that looks like this, and that has been moved, up 2 and to the left 6. So this is kind of putting all this stuff together, right? We're also doing 2 things at once. We got a couple of minutes, so let's talk about 7 all together, and then I'll leave the others for homework. So we want to look at this function. Y equals the quantity x minus 1 squared plus 3. So first we want to decide on the parent function or the function type. How do we do that? What kind of function is this? What is that graph going to look like? A square. How do you know, Blaine? Because it's squared. Yes, thank you. What's going on there other than the -1 and the +3, right? Because what we've been trying to figure out is what subtracting 1 or adding 3 would do. Those are the little changes we're making. The thing that's fundamental about that, that's going to determine how it behaves and what it looks like and stuff, is the square part. That's what the function does. That's the, thing that determines kind of what it looks like. So x squared. That tells me what kind of thing I'm looking at, right? Okay, well, I didn't really want these anyway. That tells me that I'm looking at a function that looks like this. And again, basically, when we see a square somewhere, we want to be thinking this. And when we see this, we want to be thinking square, right? Kind of tying those two things together. What has changed? What does the -1 do?
It multiplies by itself, which would change it to positive.
Well, if it was just -1 squared,
Oh,
then that's true. But it's x -1, right? And x is a variable thing. X is changing. Okay, so what does that x -1 do that x squared wouldn't do on its own? Like, how does that change things? Shifts the graph to the right. Shifts to the right one. What about the +3? Shifts up 3. Yeah, good. Now, your point about like the -1 times itself be inside the square, that does, do some work in determining what's going to happen. So like, what would this thing actually look like? Like the thing I just drew, right? But where? To the right one, and then up 3. So this point would be where? It used to be at 0, 0. Now it's at 1, 3. Right? The x coordinate went to the right. So that's from 0 to 1. The y coordinate went up. So from 0 to 3. So now it's at 1, 3.
Technically, in interval notation, you use brackets, but whatever.
I'm just marking the point.
Yeah.
Yeah, so I'm just marking the point. So points are always parentheses. Would that change the domain? No. It's a square function that's defined everywhere. Doesn't matter if you move it left, right, up, down, whatever. What about the range? Yes. The lowest point used to be 0, but now it's 3.
That's for the domain, it's the same infinity, or?
Yeah, those are, oh, sorry, negative infinity. Yeah. Yeah, sorry about that. Okay, you do the other 3, 8, 9, and 10 as homework tonight. Tomorrow we'll start right there and just make sure we're all on the same page. And then we'll add some more stuff. Okay? Y'all have a good day. I'll see you tomorrow.